So our first step in thinking about where flux integrals over surfaces in 3 dimensions come from is we're going to revisit the divergence theorem example, which was the last example that we did at the end of our last class. So in our last class, we were sort of preoccupied with trying to interpret flux integrals in 2 dimensions as double integrals of the flux density, which is otherwise known as the divergence of a vector field. And what we did was we exchanged one for the other. Well, the last example we did was an example in 3 dimensions, where I wanted to study what is the flux of this vector field, xy, 1 minus z, sine of xy, through the faces of the unit cube in 3 dimensions, so the unit cube in the first octet. And so your speculation is that what we would do is the same thing. We would compute the flux density by using the divergence, and then integrate that flux density on the now 3-dimensional region that surface bounds. And that is indeed exactly how that works. So if I want to compute the flux integral through a closed surface in 3 dimensions, I can use the divergence theorem to replace that flux integral with a triple integral over the solid region in 3 space that's being bounded by my closed surface. So that result is called the divergence theorem. And this is going to be our opportunity to get a little bit of practice with how the divergence theorem works and what it sort of tells us about the flux. So to get us started, let's jump down here in section 12.10 to this first activity where it's going to have us, ultimately, when we learn how to do all of the details and the nuts and the bolts, we're going to be able to compute the integrals on both sides of the divergence theorem to verify that they're equal to one another. But since we haven't yet gotten to the point of learning how to compute a surface flux integral yet, that's going to be tomorrow, the last thing that we do for the semester, we're going to focus here on, first of all, what should that surface flux integral mean? And then second of all, how should we compute the right-hand side of the divergence theorem, that triple integral? So in this activity, we've got a cylindrical surface, and this time it's a closed surface, so it includes the soup can label portion that's around the outside. It also includes the circular lids on the top and the bottom, right? So that makes it a closed surface. The radius is 2 and the height is 1, so they've embedded a nice little visualization right here in the text for us. Notice that they've also, on this visualization, labeled the outward directions. That's something that is going to be important for us tomorrow. It helps us to, when we do the manual calculation of outward flux, this is how we specify in those flux integrals which direction is going to count as being out as opposed to in. Remember, we had to make this decision about 2-dimensional flux yesterday when we decided that positive flux means flowing from my left to my right as I meander along the parameterized curve in the direction of the parameterization, right? Same kind of idea that we'll use for surfaces. We have to be intentional about what is the out direction that we're going to measure the flux against. And so here's a vector field that we're going to consider. Here's actually a cool 3-dimensional vector field visualization of it. So they really went all out in this section to give us some nice visuals. And so the question is there more vector field flowing into this little tuna can, or is there more vector field flowing out, or is it equal? Is there an equal amount? So that answer is given to us by the flux, the inward or outward flux from this surface. So when we do this by direct computation tomorrow, we're going to have to parameterize the surfaces and specify those normal directions explicitly. But that's not the direction we're going to take with it today. Because we want the divergence theorem to bail us out. Right? We want to trade out that purple flux integral here because we have a closed surface. We want to trade it out for that red triple integral that we see down here on the bottom right. So that is going to be nothing more than doing parts C and F and G, I suppose, of this activity. This is activity 12.10.2. I haven't written this up in the activity stream for you yet, so let's go back to the 12.5, the place where we left off, and I will paste this problem at the bottom of your 12.5 to let us have the ability to get resumed here.